So without further ado, Andrew, are you ready to get started? Because I'm about to introduce you.
Yeah, I'm all set.
All right. So for those of you who don't know Andrew Wilder, he is your go-to expert for microphones, conferencing systems, and DSP. So he's been working in the field for about 15 years. His experience ranges from live sound, reinforcement to corporate installations. Before SFM, Andrew was a lead installer of AV presentation systems and unified communication systems and network AV solutions in the Greater Toronto area. When he's not delighting us with these wonderful presentations, Andrew loves to spend his time outdoors, and he's never without a good cup of coffee. He's a pleasure to work with, honestly. So I hope you enjoy this time with us. Over to you, Andrew.
Okay, well, thanks for that, Lisa. Yeah, I always can go for a good cup of coffee anytime, any day. That's definitely one of my favorite things to have. But let's jump right in today. So you're here to learn a little bit about AAC. So we're going to kind of go into what is acoustic echo cancellation, talk about where, when, and why we want to use AAC. We'll go through some of the terminology on AAC so you understand it. And we'll cover at the end there a bit of proper setup for voice lift applications, because that's the one I find a lot of people struggling, especially if you're new in AAC. So again, at any time, please send questions to Lisa so she can stop me if something doesn't come across very well. We want to make sure everybody has a good understanding when we get done with the webinar. So what is AAC? AAC is acoustic echo cancellation, is the process of removing the return echo of the far end audio while preserving the sound of the near end audio. So when we configure AAC at the near end, you're canceling the echo for the far end participants. This allows the far end participant to not hear their own echo. The far end's AAC is what allows you to participate in the call without hearing your echo. So currently in this case, if I consider myself the near end and I'm programming an AAC component, I'm canceling the echo for you so you don't hear yourself come through at the far end, right? You don't hear your own echo return. And vice versa, your system right now, so your Zoom that you've joined in is actually canceling echo so that I don't hear myself come back through my speakers. And that's the basic process of what we're looking at. It's simplified form. So where do we use it? We're going to use it pretty much anywhere we're doing collaboration. So that could be a boardroom, huddle rooms, training rooms, and definitely new times have brought us into at-home situations where people are expanding on their at-home offices, right? When we need to apply it, well, that's going to be any time we're using VoIP or POTS telephony, okay? So those are your physical connections. POTS is that plain old telephone system, simple analog telephone like you have at home right now. VoIP is, typically using SIP, that's over the network telephony, right? So you're connecting through telephone calls. We're also going to use it when we're dealing with dedicated video conference systems. So things like Cisco codecs or YaLink or LifeSize. Any of those require some AAC. A lot of them have it built in to work with their own microphones. However, when you start considering using microphones that aren't part of the brand and you start adding ceiling microphones from other companies, then you need to consider an outboard DSP to handle the differences and expand on it that way. And one of the more common ways that we're seeing them now is using through soft codecs. Soft codecs are things such as Blue Jeans, Zoom, like we're using right now, Teams, and many, many more. So those are really the three major areas that you're going to see a lot of AAC when you need it. So why? So why do we need AAC? So let's take a look at the basics of how AAC works. So in any conference, we've got a near end and a far end, right? And every near end or far end, they both have microphones and speakers. Now maybe that's through a headset, or it's an in-ceiling speaker and microphones on a desk, or a ceiling speaker, but there's some sort of combination of a microphone and a speaker at each end. The idea with AAC is that we're going to send audio from the microphone to the opposite end's speaker so that the other person can hear them. Without AAC, what happens is the audio will go out of the speaker into the microphone and return back to the other person, and they hear themselves. That's where you get the echo. So just like you can see on the screen now, the far end speaker talks into their mic, it goes out of the near end speaker and hits the near end microphone and returns back to create an echo. So when we jump right into how AAC works, we got a nice little algorithm here, and I'm going to go ahead and bring up my laser pointer to go through this. So we've got a far end talker, okay? They're going to call into a system. Their audio needs to come through the system and out of the near end speaker. At the same time we do that, that audio needs to go into the AAC component. And inside that AAC component is an adaptive algorithm, right? And it's going to take a reference of that audio. So the audio bounces off the wall, goes back into the microphone, typically a little bit later, sometimes at the same time as the near end talker. So all that audio goes back into the microphone and through the process to return out the far end speaker. If we don't have this adaptive algorithm, that's where the echo cancels. However, because we're sending in that signal to the AAC component, it will take a look at it and say, hey, that matches. Don't let that go back to the far end. And it essentially throws it away into the garbage. Then followed through there, it goes through nonlinear processing, noise reduction, maybe some comfort noises added, and then you've got an auto gain control, right? Hopefully this is making sense to you right now. I'm going through it fairly quickly, but at the same time, I want to make sure everybody's got a good understanding. So please raise your hands at any time if there's a question. So let's go through some of that terminology that we just talked about. So first off, we got the near end, right? So again, that's the room with AAC to cancel each other's echo on the call. The far end is the room on the call with near end. With AAC and near end, and room cancels far end echo, right? So near end is me, you're the far end right now for me. The opposite, if you're the near end, I'm your far end. That's the simplest way to explain that. The AAC reference, that's the signal we want the AAC algorithm to remove from the near end mics. So again, that's that far end audio being sent into the AAC, that's the reference, okay? So when we look at any sort of AAC in general, they all have noise reduction. Noise reduction, or NR, it reduces the level of constant noises like HVAC and wind that's transmitted by microphones, okay? So constant noises, it doesn't get rid of tapping on a desk or somebody who clinks their silverware or a glass, because that's not a constant. It's typically for wind or HVAC. Tail length, if you're not sure what the tail length is, you'll probably see that in a lot of the open architecture platforms. That's the latest possible reflection that can be canceled. Typically, it will be in milliseconds. Most of them operate around 200 milliseconds. Some of them, I don't know what they advertise at, but the brands I typically work with operate around 200 milliseconds. And what's happening is that AAC component is holding the audio for about 200 milliseconds so that it can reference it as it bounces off the walls and comes back into the system. When we get into the next part of the AAC component, it goes through residual echo, otherwise also known as nonlinear processing, or NLP, and there's a few DSPs out there that refer to it as double talk. That removes error signals after AAC. So those are even later reflections, longer than the tail length of the AAC algorithm, right? So we think about how an audio reflection works in a room. It comes out of that speaker, bounces off the wall and goes back into the mic, but it always doesn't always bounce off the wall in a direct line. So it bounces off the wall in multiple different directions. And some of those audios come back into the microphone at much later time than 200 milliseconds. So that's where we start adjusting that NLP, or residual echo. We increase that to get rid of those late reflections. And a few other things we want to discuss before we move forward. So voice lift, what is voice lift? That's the near end microphones sent to the near end speakers, okay? Voice lift restores the natural speech level of the talker. That part's key to understand. A lot of people confuse voice lift with sound reinforcement. Sound reinforcement is something typically you'd see at a conference where you have some speakers and it's taking a presenter and making them quite loud in the room. If a voice lift is set up properly, you won't even know that the speakers are on, but it will restore the natural level so that if I'm sitting 30 or 40 feet away from the person talking, it feels as if I'm sitting only 5 to 6 feet away. If you turn those speakers off, you would notice that it wasn't working. As long as it's on, you won't even notice the speakers are on. That's the best way to set up a voice lift system. We'll refer to mix minus references. That reference to a microphone receives all audio going to the near end speaker except itself. So that's the mix minus itself. I'm using it in the term as a reference, but there are also mix minuses for zoned outputs. And when we look at a zoned output in a large room where there are distinct speaker circuits, so that's multiple feeds to different speakers, for voice lift, microphones are mixed to needed outputs to maximize gain before feedback. So we think of using zoned outputs when we're going to send those near-end mics back into the room, because what we're going to do is be able to get the proper level for voice lift without causing feedback in the room, right? So if we get that all set up correctly, then you have a really nice system that doesn't have echo, and at the same time will allow voice lift in the room so that nobody has a hard time hearing each other. Hopefully this is all making sense to you right now, and please save some questions for the end or throw them in now. So let's take a look at how microphone processing works when we're in AAC. So we want to avoid processing between the input of microphones and the AAC component. Basic equalization is fine, dynamics are bad. So we don't want to put compressors or any other dynamics pre-AAC. The image on the screen you can see is of a fixed architecture platform. You'll notice that there's a mic input followed by a parametric EQ right before it goes into the AAC. That's okay, but there are no dynamics prior to that AAC component, right? So one of the nice things about fixed architecture is it's already doing all of the thinking for you in the sense that it doesn't allow you to place something prior to the AAC that shouldn't belong there. Excuse me, we're just gonna have a quick drink of water. So what should go into an AAC reference? The AAC reference should receive anything that's sent to the near end speaker. It needs to be in the reference. Things that are going to go there are your far end audio, so the input from the VoIP, the input from the POTS, maybe that's a USB soft codec input coming into the system. Those are all going to go to the reference. Your program or source audio should also go to the reference. Why? It's coming out of the speakers in the room. And that way it can cancel it and doesn't allow it to go back through. And definitely microphones used for voice lift. In many situations I see designs that come through, they're experiencing some bit of echo or some weird digitalization. What's happening there is if you're not canceling the mics going to the voice lift properly, it starts to cause issues within your AAC. It takes a bit longer to build that process, but in the long run, it's certainly worth the time to do that. So what about fixed versus open architecture? I kind of hinted that there are some differences already. So when we take a look at fixed architecture, most of the times you're just choosing where the reference is coming from, whether that be the USB input or maybe you've got it to an output, you're simply assigning the reference. And a lot of times your fixed architecture DSPs will only have a shared reference, right? What you put into that reference is based on the output. Maybe there's a matrix mixer in the fixed architecture that allows you to assign different inputs to the output or vice versa. Okay, so when we think about an open architecture DSP, you typically get an element like you see down here in the bottom right corner, right? It's a block with a bunch of pins that you need to wire up. And in the reference, if it's a shared reference, you need to build some sort of mixer that sends all the audio that's going to come out of the local speaker to that reference pin. The ideal spot to take that reference is right before the audio leaves to go out of the speaker element of the DSP. Okay, you want to get it as close to the output as possible so that you're not dealing with any changes in the audio. So if you put it too early and then you start putting compressors or EQs on it, after you've taken the reference, you're going to have some differences in the audio as they go back into the system, which is going to cause your audio to not match, right? So if I send out my signal and then I take the reference and I change the reference so that it's been pitch shifted or compressed, well, imagine that it doesn't look. So it's like taking a square. I want to send a square out, but I send a square to the reference and I change it to a triangle. Well, a triangle and a square don't match. I'll get rid of the triangle and that little bit left from the square will sneak through and cause echo, right? So it's kind of like sending different shapes. So when we look at that shared versus independent reference, if we look at local microphones only going to the far end, we use a shared reference, right? So most conferencing systems, especially when you're looking at smaller rooms, huddle rooms, basic boardrooms, if you're only sending the local microphones to the far ends for the teleconference system, then you can use a shared reference because those mics are not going to cancel each other out. So we just use that typical shared reference. But what happens if we start thinking about voice lift? So if you tend to send any local microphones to the near end speakers, use an individual reference per microphone. So you can see in the two different examples, suddenly I'm going to send the microphones to the near end. Therefore, I want to give them each their own reference. And this is where you get into mixed minus and zoned outputs. So why don't we dive right into that? And this will take a bit of time to go through. I'm going to try to make sure I go through it slowly so that we all get through this one. So here's what we're looking at. This is a voice lift application, right? We've got AAC, and we need to also send those mics to the near end. So the microphone of the audio gear needs to, let's see here. Yeah, so we need to send the mics to the near end from a different pin or a different source than you would to the conference pins. So you can see I've circled some different outputs on this DSP platform. Those pins don't come off of the conferencing feed. That means they don't get that delay created by the AAC. The delay is created because it holds the audio for 200 milliseconds. You remember that tail length we talked about. So we're going to send them from a different output. Some platforms may not have a separate set of pins in their AAC component. In that case, you'd really want to take them right here from the input, right? To avoid getting the delay created by the AAC component. So that's what we're going to do to send them to the near-end speakers. If we move on a little bit further, you can see that we need to also give them individual references. So you'll notice that I've got different reference pins going in for each microphone. I've highlighted microphone reference number 1 is in blue there, and you can see it's coming from a separate mixer, right? Right down here is my AAC reference mix. Inside that mixer, I've set it up so that microphone reference 1 gets everything it needs except for itself, and I'm going to show you that in just a few moments. The other thing we need to think about is when we're going into our near-end speakers is how we set it up so that we have a zoned output, right? Why do we do zoned outputs? That's going to give us a greater gain before feedback, okay? So inside here, I'm sending microphones to the different zones that they would need it. I don't really need to send the microphone audio to a speaker that's covering the person right next to me, right? Because they should be able to hear me just fine. But if you're at the other end of the table, you may want a little bit of increase in the volume of what I'm saying so that you can understand what's coming out without straining to hear. Is this making sense? So what you're looking at in this platform is a mixed minus zoned output, open architecture DSP design, right? And in the end, if you need this, you can obviously reach out to us at TAG and we can even supply you with this design to help you get through and understand it further down the road. So let's take a look at what's in the mix minus reference. Here is that mix minus reference, okay? So we can see at the bottom, this DSP has the inputs across the bottom, meaning that the vertical column is the input, treated like a live sound console. There are other DSPs that bring your inputs in from the left. In this case, we're going to refer to one that uses the inputs from the bottom. So we've got our input here in the vertical column, that's microphone input 1. And you can see microphone 1's reference going out. So you notice that I didn't assign microphone 1 to itself, right? But everything else going into microphone 1's reference is there. Microphones 2 through 10, plus the far end audio is coming in here. If I had any program sources, that would also need to be assigned to that reference. And if you follow the blank spots right down through the design, you'll notice that microphone 2 doesn't get itself, 3 does not get itself, 4, and so on and so forth. So what we're doing is a mix minus. The reference gets everything it needs going out of the speakers except for itself so that we don't cancel that microphone, right? I wouldn't want to talk and then have myself cancel. And those of you guys who don't know what that sounds like, it'd be like this. You're talking to the microphone, but in the audio, it starts canceling itself. It cuts through, like, gets a little bit choppy, like when you have a bad bandwidth connection on a Zoom meeting or a Teams meeting or any other. Not happens very often, but it will create that sort of effect, okay? Zoned outputs, which is kind of really the last section I need to get into without going too deep. A zoned output system allows us to create that gain before feedback. And what we look at here is, again, here's microphone 1 in the mixer, right? And you hear my zoned outputs, zone 1, 2, 3, and 4. You'll notice that zone 1 and 2 are empty, but microphone 1 goes to zones 3 and 4. So if we refer down to that boardroom layout I created, microphone 1 is here on the table. This is zone 1 at the front and zone 2. The person sitting next to them does not need any amplification. They should be able to hear them just fine. But if we think about things like inverse square law, the person at the other end of the table is probably going to feel like they're twice as far, 3 times as far away, depending on how long that table is. So we send the audio from mic 1 to zones 3 and 4. And that also means that this microphone is much farther from the speaker, which in turn allows us to increase that gain so we don't cause feedback. Is that making sense to everyone? That's kind of the gist of AAC without going overly deep into it. We're getting into it. Does anybody have questions? We can jump right into questions. I can back up to the designs and go through it. At this point, if Lisa's okay with it, I'd be okay. You can open your mics even and ask your questions live if you would like. Oh, you're muted, Lisa.
No. Thank you, Andrew.
I know that's really fast, but that's the basics of AAC without going too in depth. So does anybody got any questions on AAC, anything that they're working with, they're concerned about? You're okay to bring up particular brands with me. I know probably 90% of the DSPs that are on the market right now.
I have a question for you, Andrew. It's Richard.
Yeah.
A couple of slides ago, you had, I think, input 7 not routed to possibly output 9 or something, and I didn't get a chance to really look at it.
Sure, was it
Why
this one?
is that? So output 9, input 7. You mixed minus that one.
Oh, right here. Yeah,
Yeah.
you know what? That's just a mistake. Thank you for catching that.
Yeah, no
You know, it's
problem.
one of those things, Richard, where you stare at these designs so often and create them so quick, it's easy to miss one little mark. So I'll update that for the next time I use this and recreate that image. But yeah, I would have put that in there as well. That should be in there. You really should only have the microphone not going to its own reference, right? So in this case, there may be a slight echo created from microphone 7 on output 9. Unlikely because it's being canceled everywhere else, but best practice would be that I'd have that cross point set.
And it'll be the case as well, I think, for input 10, output 6.
So there's 2 of them. You guys got good eyes. I went through this so many times and missed those. Let me write that down real quick.
Not because you don't know or understand, just, you probably quickly designed it.
Yeah. So that's N7 to out 9. N10 out 6. Are you guys, a couple questions for you guys maybe. Are you doing a lot of voice lift with the mixed minus and zoned outputs right now? Are you struggling with that? Have any questions on getting AAC tuned properly? Looks like we're pretty good, I guess.
So if ever you want to continue to chat with Andrew afterwards, I'm going to send a link in the chat box to everyone where you can reach the tag group. So it's tag.sfm.ca. So you can take note of that, and Andrew can share some of his slides or talk to you about specific issues that you're having or additional questions. If no one has any other questions, thank you everyone for joining. And next week is our next webinar. Andrew will be covering audio gain structure, and the link is in the chat box as well. Thank you. Thank you,
Thanks,
Michelle.
everyone.
Thank you, Keith. Have a good Friday. Have a good weekend. Bye, Paulo. Bye, James.
Thanks, everyone.
Bye, Richard.
Bye now. Thanks so much.
Take care.
Thanks, Richard.
You're welcome.
Bonjour Jean-Robert.
Merci.